Hi, I'm Neil deGrasse, and today I will tell you 100 amazing facts about dark matter you don't know. Subscribe and let's start. Number one, most matter is dark. It does not emit or reflect light. We catch it by its gravity tugging on things and bending light. Dark matter acts like the universe's scaffolding, shaping galaxies. Clusters and the cosmic web. Normal matter is just a small slice. Dark matter is the heavyweight champ we still cannot see directly. Number two, Fritz Zwicky's missing mass. In the 30s, Fritz Zwicky studied the Coma cluster and found its galaxies moving so fast the cluster should have flown apart. His fix was unseen mass adding gravity, stuff we cannot see. Using a simple gravity budget, the virial theorem, he calculated far more mass than starlight showed. He even named it Dunkel Materie, known as dark matter. Launching the modern missing mass problem. Number three, Vera Rubin made it undeniable. Vera Rubin measured flat rotation curves in many spiral galaxies with outer stars orbiting as fast as inner ones. That only makes sense with huge, invisible halos. Her repeatable results showed this was not a Coma one-off. Dark matter is widespread across galaxies and clusters. Rubin turned a hint into a robust mainstream observation. Number four, why we know it exists. When two clusters collide, the hot gas slows and glows in X-rays, but the main mass keeps going. The gravity map ends up offset from the glowing gas. That mismatch is hard to explain without a big cloud of unseen matter, also called dark matter, wrapped around each cluster. Number five, gravitational, not luminous. Dark matter does not emit, absorb, or reflect light, so telescopes cannot see it shine. It reveals itself through gravity, bending light and sculpting galaxies and clusters into the structures we observe. Map distortions and orbital speeds and you uncover big, invisible halos, doing most of the heavy lifting. In short, no glow. All pull dark matter shows up through gravity, not light. Number six, not spread evenly. Dark matter is clumpy, not smeared out. On huge scales, it threads the cosmic web in long filaments. Inside galaxies, it gathers into halos with uneven density, plus lots of little sub-halos buzzing around. Those halos tend to be denser toward the center, then thin out with distance. Number seven, the cosmic scaffolding. Because dark matter barely interacts, it clumped first as the universe expanded. Those clumps linked into a web of filaments, the scaffolding of structure. Later, normal matter fell into those gravity wells, cooled and lit up as galaxies and clusters. In simulations, you mostly see dark matter maps. The shiny stuff simply follows the wells it makes. Number eight, no dark planets. Dark matter does not interact with light, so it cannot radiate heat the way gas does. No cooling means no collapse into disks. Stars or planets, just big diffuse halos and small subhalos. It only clumps by gravity, staying puffy compared with dense, shiny stuff. Galaxies form when normal matter falls in, cools, and lights up. Dark matter supplies the skeleton, not the skin. Number nine, heavy enough to clump. If dark matter particles were too light and zippy, small structures would smear out and dwarf galaxies would be rare. Observations show lots of small stuff, so dark matter must be cold or slow-moving and massive enough to gather by gravity. That is why one big candidate class is WIMPs, weakly interacting massive particles. Massive helps them clump. Weakly interacting keeps them invisible to light. Number 10, the bullet cluster smoking gun. Two galaxy clusters crashed, the hot gas slammed on the brakes and piled up. But the mass map kept going. Result, the gravity peaks sit offset from the glowing X-ray gas, pointing to a big chunk of invisible matter. Stars mostly sailed through, gas got dragged, and dark matter behaved like collisionless stuff. Short version, the glow stayed and the gravity moved, so something invisible carried most of the mass. About 27% of the universe is dark matter, roughly 68% is dark energy, and only about 5% is ordinary stuff. The tiny slice we can see. Together, those unseen pieces add up to about 95% of all cosmic content. These fractions come from precision measurements of the CMB, BIO, and supernovae. The bright universe is just the tip of the iceberg. Number 11, the cosmic pie. About 27% of the universe is dark matter, roughly 68% is dark energy, and only about 5% is ordinary stuff, the tiny slice we can see. Together, those unseen pieces add up to about 95% of all cosmic content. These fractions come from precision measurements of the CMB, BIO, and supernovae. The bright universe is just the tip of the iceberg. Number 12, percentages can shift. Cosmic fractions get refined as new data roll in from CMB, BIO, and supernovae, so the exact percentages move a bit year to year. One thing stays solid. Dark matter outweighs normal matter by several to one, with total matter about 1/3 of the cosmos and the rest dark energy. Planck set the baseline near 31% matter. Newer surveys keep it in the same ballpark. Numbers sharpen, the hierarchy remains. Number 13, cold versus warm dark matter. Cold dark matter moves slowly, so it keeps tiny clumps and builds lots of small halos, think many dwarf galaxies. Warm dark matter moves faster. Its free streaming smears out the tiniest clumps, leaving fewer small galaxies. A classic warm candidate is KeV sterile neutrinos, which would blur those fine structures. Astronomers test this by counting dwarfs and using the Lyman alpha forest. So far, data mostly favors cold. The key difference is early universe speed, not literal temperature. Number 14, not mostly black holes. Could dark matter be tons of tiny black holes? It is a cool idea. But most mass ranges are ruled out. Microlensing surveys do not see the brightening you would expect if black holes made up all the dark stuff, and CMB tests also push back because accreting black holes would have left a signature. Primordial black holes might exist, but they likely make up only a small slice of dark matter. Number 15, not antimatter. Antimatter, meeting normal matter, annihilates and blasts out radiation, often high-energy gamma rays. If dark matter were mostly antimatter, we would see lots of those signals across the sky. Instead, dark matter stays electromagnetically invisible, no glow and no absorption, showing up only through gravity. Space experiments hunt for tiny hints, but the sky is mostly quiet. Number 16, self-interacting dark matter. Some models let dark matter particles bump into each other a little, trading energy and smoothing dense cusps into softer cores and galaxy centers. That can help explain why some dwarfs and spirals look less peaky than pure collisionless models predict. The scattering must be very weak. Cluster collisions limit how often dark matter can hit itself. Astronomers test this by mapping halos in dwarfs and clusters for inner shape clues. Number 17, no link to DNA changes. There is no evidence that dark matter alters human DNA. It barely interacts with ordinary matter at all. Direct detection and cosmology limits imply ultra-rare hits far below everyday background radiation. Ideas about exotic dark sector particles affecting biology remain speculative and unsupported. Dark matter streams through us quietly. Our cells and DNA do not notice. Number 18, lensing maps the invisible. We see dark matter by how its gravity bends and distorts light from background galaxies like nature's X-ray for mass. Big bends and arcs are strong lensing, tiny shape tweaks across many galaxies are weak lensing. Both let us reconstruct mass maps that often reveal more mass than starlight shows, tracing dark halos in the cosmic web. Hubble pioneered detailed cluster maps, and new surveys scale this to vast swaths of sky. Number 19, dwarf galaxies are labs. These tiny galaxies are dark matter dominated, so their star motions trace the halo's gravity with less noise from gas and disks. That makes them perfect to test halo shapes. Core versus cusp, particle properties, cold versus warm, and even to hunt for annihilation or decay signals. Because they are faint and simple, small model changes show up clearly in their velocity dispersions and mass profiles. Number 20. Structure growth as a test. As the universe ages, tiny clumps of matter grow under gravity. How fast they grow is a fingerprint of both dark matter properties and the laws of gravity. Measure that growth with weak lensing and redshift space distortions. If structures build too slowly or too quickly, models get ruled out. Cold, dark matter, and general relativity make specific testable predictions. Alternatives like warm dark matter or modified gravity change the growth rate. Big surveys map this growth across time to see which picture matches the real cosmos. Number 21. Many ideas point to WIMPs. A lot of dark matter models start with WIMPs, weakly interacting massive particles that are heavy, slow, and mostly feel gravity. They are classic thermal relics from the early universe and fit how structure forms. That is why underground experiments in the LHC keep targeting them. So far, there is no confirmed hit. But WIMPs remain the benchmark. Number 22, other candidates on the table: axions, ultralight wave-like fields, sterile neutrinos, and even primordial black holes are all contenders. Some would have complex interactions or much higher masses, changing how they form and how we might detect them. Dark matter's identity could be weird and heavyweight or whisper light and wavy. The search keeps all doors open. Number 23, gravitino, a stealthy option. The gravitino, the supersymmetric partner of the graviton, is a super weak dark matter candidate that would be effectively invisible in detectors. Its interactions are so tiny that even a small effective charge in speculative models would not make it glow. Formed in the early universe and very long-lived, it could quietly account for the dark matter, a super weak particle hiding in plain sight. Number 24, not in the standard model. The standard model has quarks, leptons, photons, and gluons, but none behaves like dark matter. Explaining the missing mass needs new physics, such as WIMPs, axions, or sterile neutrinos that live beyond the standard model. This is why the LHC and underground detectors keep hunting. Dark matter points to physics we have not discovered yet. Number 25, LHC constraints from missing energy. At the LHC, dark matter would slip out unseen, leaving missing transverse energy that recoils against one visible particle. A jet, photon, Z, or Higgs, the mono-X idea. Atlas and CMS have not seen extra events, so they set upper limits on masses and interaction strengths. With 13 TeV data, typical mediator masses are pushed into the TeV range. Each null result trims viable WIMP space and guides new searches. Number 26, composition versus energy. Cosmic budget check, about 31% is matter, roughly 5% normal and 26% dark, and the rest is dark energy that drives acceleration. Those fractions come from sky measurements, with Planck pinning the matter slice near 0.31. The LHC does not weigh the universe, it hunts particles. Together the sky sets the split, while colliders tell us what dark matter can and cannot be inside that slice. Number 27, dark matter can warm planets. Dark matter can warm planets. Imagine tiny dark matter particles falling into a planet's center. If two meet, they can collide and turn into energy like a tiny heater. This adds a little warmth that doesn't come from the sun, so an old rogue Jupiter wandering in the dark could be warmer than expected. Astronomers look for extra heat to test this idea. Number 28, we map invisible clumps by tearing star streams. Some stars travel in long, thin rivers across the sky called stellar streams. When an unseen dark matter clump passes by, it tugs and makes a gap in the stream. Those gaps are like footprints left by something invisible. By measuring their size and shape, scientists can weigh the hidden clump. Streams like GD1 act as cosmic tripwires for dark matter. Number 29. Dead stars can sniff dark matter. Neutron stars are tiny, super dense leftovers of big stars. They can trap passing dark matter particles inside. If those particles collide, they release heat, warming the star a bit. In extreme cases, they might even make the star unstable. Cold old neutron stars are perfect to check for this extra warmth. If we find it, the scent points to dark matter. Number 30, why dark matter matters. Remove dark matter and galaxies fly apart. There is not enough visible stuff to hold fast orbits. Extra gravity from dark halos keeps galaxies and clusters bound and lets the cosmic web grow. This hidden mass is the majority share of matter, so it sets the stage for gas and stars to form. No dark matter means no stable galaxies and no grand structure. Number 31, is dark energy like dark matter? No, dark matter clumps and holds galaxies together, while dark energy is smooth and drives accelerated expansion. Dark matter shows up through gravity and lensing and motions. Dark energy acts like a negative pressure that speeds space apart. Do not confuse it with inflation, which was a brief early burst. Today, dark energy rules the expansion. Number 32, dark matter slows. Dark energy speeds up. Dark matter's gravity pulls things together and slows expansion, most strongly in the early universe. Dark energy provides a smooth push that accelerates expansion today. Think of a tug of war. Matter gives deceleration. Dark energy gives acceleration. The pull still shapes structure, but the push now wins on large scales. Number 33, underground hunts in quiet labs, deep under mountains, detectors like LZ, Xenon and T, and super CDMS avoid cosmic rays. They wait for a rare bump, a dark matter particle nudging a nucleus and leaving a tiny flash or vibration. LZ and Xenon and T use liquid xenon time projection chambers. Super CDMS uses cryogenic silicon and germanium to hear faint phonons. Years of quiet can define the strongest limits. Number 34, Null results sharpen limits. Silences data. Recent LZ exposures in xenon and T runs reported no WIMPs, so the limits tightened again. Each no hit slices away more parameter space, pushing down spin-independent cross-sections around tens of GeV. The result is fewer hiding spots and a clearer map for next-generation detectors. The search becomes more focused. Number 35, ultralight axions, the fuzzy idea. If dark matter particles are ultralight, their de Broglie wavelength can span kiloparsecs, so they act like waves. That wave nature washes out tiny structures and makes soft, solitonic cores in galaxies. On large scales, the behavior looks like cold, dark matter, but differences appear in dwarfs and in the early universe. Lyman alpha data and galaxy cores are boxing in the allowed masses. Number 36, local density is tiny. Near the sun, dark matter is very thin, about 0.3 GeV per cubic centimeter, roughly 1 proton spread over 3 cubic centimeters. At that WISP level density, interactions are so weak that there is no direct hazard to humans. It matters on galactic scales where huge volumes add up gravity. Locally, it is just a gentle background. Number 37, what gas and dust tell us? Hot gas in galaxies and clusters glows in X-rays, so X-ray telescopes can map where normal matter sits. Dust absorbs visible and ultraviolet light and re-emits in the infrared, which is why it shines in web images. Gas and dust leave clear electromagnetic fingerprints. Dark matter does not. It shows up only through gravity. Number 38, the name is modern, the idea is older. The label dark matter took off in the 20th century with Zwicky's 1933 Dunkel Materie. But the puzzle is older. Poincaré wrote in 1905 about matière obscure buildings on Kelvin's dark bodies, and Oort in 1932 argued the Milky Way held invisible mass. Zwicky clinched the point with the Coma cluster where light did not match gravity. Unseen matter had to be shaping galaxies. Number 39, hard to tinker with, and that is fine. If dark matter barely interacts, magnets, lasers, and chemistry will not grab it. Gravity is the only practical handle, and it is too weak to manipulate in a lab. Present technology cannot poke dark matter directly. The same near invisibility that frustrates experiments also means no practical hazard. Number 40. The CMB is a fingerprint. The CMB carries acoustic peaks whose heights and spacing only make sense if dark matter was already present. Adding extra gravity. Without it, the hot and cold spot pattern would be wrong in amplitude and scale. Tiny lensing distortions of the CMB also map dark halos. The precise wiggles are a built-in signature of dark matter in the early universe. Number 41, BIO is a dark matter fingerprint. The universe carries a faint BAO ripple, a preferred spacing in galaxy positions left by early sound waves. Those ripples form in ordinary matter, but their scale and strength only make sense with extra dark matter gravity shaping the wells. By measuring BAO across time, astronomers confirm a cosmos where dark matter dominates normal matter and map how expansion evolves. BAO are a built-in standard ruler and a clean signature of dark matter's role in structure formation. Number 42, dark matter is real. What is real in physics is what repeatedly explains data and predicts new results, even if it is invisible. Dark matter fits, it bends light, sculpts galaxies and clusters, and its predictions keep matching new surveys. Scientific realism says we are justified in believing in unobservables when our best theories keep working. From lensing maps to CMB and BAO patterns, the same unseen mass keeps showing up. Invisible, yes. Unreal, no, its gravity keeps passing the tests. Number 43. Minuscule dose for humans. Known dark matter limits say interactions with atoms are ultra rare and ultra weak. So the energy deposited in our tissues is tiny. Even with the standard local density, expected hits are far below normal background radiation. Modern experiments keep shrinking the allowed interaction strength, pushing doses downward, not up. By current bounds, dark matter's contribution to human radiation exposure is negligible. Number 44, dark matter likely enabled us. Even though it is invisible, dark matter clumped first, laying down the gravity wells that shape the cosmic web. Gas fell in, cooled, and lit up as stars and galaxies, preconditions for planets and eventually life. Take away those dark halos, and the universe forms too slowly and too loosely for the rich structures we see today. Number 45, mass where the light is not. In cluster smash-ups, the hot gas, which is most of the normal matter, slams to a stop and glows in X-rays. Gravitational lensing maps put most of the mass offset from that gas, lined up with the galaxies that sailed through. Repeat this across multiple collisions, and you get the same story. A big chunk of mass does not behave like normal matter. An additional invisible component, dark matter, dominates the mass in these systems. Number 46, cosmic web scaffold. On the biggest scales, matter forms a cosmic web, long dark matter filaments with galaxies lighting up the densest crossroads. Supercomputer runs grow this web from tiny early ripples, showing galaxies tracing an underlying dark skeleton. Sky surveys like SDSS map these patterns across billions of light years, matching the filamentary structure predicted by simulations. The bright stuff follows the gravity blueprint laid down by dark matter. Number 47, galactic rotation 101. If galaxies had only visible stuff, outer stars should slow down with distance. Observations show flat rotation curves. Outer stars orbit just as fast as inner ones. That mismatch means extra gravity is at work, pointing to a huge, unseen dark matter halo around each galaxy. The light says not enough mass, the speeds say far more, so we add dark matter to make the math, and the galaxies hold together. Number 48, dark matter's impact on light. While dark matter is invisible, its presence is inferred through its gravitational effects on light. A notable example is the observation of a rare Einstein cross, a phenomenon where light from a distant galaxy is bent by the gravity of a massive intervening object, creating multiple images. In a recent discovery, astronomers observed an unexpected fifth point of light at the center, likely caused by a massive blob of dark matter, providing a unique opportunity to study its distribution. Number 49, dark matter could accumulate in exoplanets. Theory says Jupiter-sized worlds can slowly capture passing dark matter, letting particles settle toward their cores over billions of years. That buildup could tweak internal heat, magnetic fields, or, in extreme cases, even trigger compact collapse, turning giant planets into tiny laboratories for dark physics. With thousands of hot Jupiters known, astronomers now treat exoplanets as test beds for dark matter ideas. Number 50, dark matter with underwater ears. Ultra-heavy dark matter might dump a burst of energy as it plows through seawater, launching a pressure pulse that hydrophone arrays can hear. New studies show large underwater acoustic networks, originally pitched for neutrinos, could scan unexplored mass and cross-section ranges by listening for those thermoacoustic waves. It is a fresh, complementary path alongside underground tanks and space telescopes. Wait a minute, my friend, 50 facts already. If you like the video, you can subscribe. Number 51, a hidden mirror world. Some models place dark matter in a parallel mirror sector with its own particles and forces that hardly talk to us, except through gravity. Such hidden sectors can naturally explain why dark matter is abundant yet invisible. And they give concrete predictions for cosmology and particle searches. Ongoing work maps how a mirror world could fit CMB lensing and structure data. Number 52, dark matter and monster black holes. Dark matter builds the deep halos where gas pools, helping seeds feed fast and grow into supermassive black holes. In some ideas, dark matter's own behavior speeds this up. Ultralight fuzzy cores or self-interactions can trigger early core collapse that plants a black hole. JWST and X-ray finds of very early, rapidly growing black holes fit a picture where dark matter kickstarts and sustains their growth. Number 53, standard cosmology needs dark matter. Run the universe without dark matter, and galaxies do not form right, and large-scale structure comes out too flimsy. With dark matter in the mix, tiny early ripples grow into halos and filaments, matching galaxy surveys and CMB and BAO patterns. This is why lambda CDM, cold dark matter plus dark energy, is the baseline model that best fits the data. Number 54, tidal streams test halos. Long, skinny stellar streams like Sagittarius, Gideon, and Palomar 5 act as tracer paint in the Milky Way's gravity field. Their bends, widths, and precession reveal the halo's shape, spherical, oblate, or even triaxial, and how lumpy it is. By fitting stream orbits, astronomers map the dark halo's geometry and spot perturbations from dark matter subhalos. Stream shapes are a clean, real sky probe of the dark halo around our galaxy. Number 55, the Hubble tension hint. Two top methods disagree on today's expansion rate. Early universe data says about 67. Local measurements say about 73. That stubborn gap could be a clue to new physics, such as early dark energy or interacting dark matter and dark radiation, not just measurement error. Recent JWST work backs the local side, and new surveys test whether tweaks to dark matter or dark energy can bridge the split. The mismatch might be the universe whispering that the model needs an upgrade. Number 56, dark energy as a cosmological constant. A simple picture treats dark energy as Einstein's constant, a constant energy density of empty space. In this model, space itself has a steady push with negative pressure, making cosmic expansion accelerate. The constant does not clump like matter, it stays smooth, so structure grows more slowly while distances stretch faster. It is the baseline in today's lambda CDM model, with alternatives like quintessence tested against it. Number 57, danger needs exotic physics. To harm us, dark matter would need much stronger interactions than today's data allow. Direct detection runs put ultra-tiny upper limits on how often it can hit normal matter. Astrophysical tests such as the CMB and lensing also squeeze exotic couplings. Anything large would have left clear sky fingerprints. With current evidence, dark matter streams through us harmlessly unless future discoveries reveal a far stronger, very exotic interaction. Number 58, built deep to stay quiet. Dark matter detectors are placed far underground to block cosmic rays that would swamp tiny signals. They also use ultra-radio pure materials and strict cleanliness to cut natural radioactivity that creates background noise. Layers of passive shielding, water, polyethylene, copper, and lead, plus clever designs keep the instruments ultra-quiet so a rare event can stand out. Go deep, go clean, go quiet. That is how you listen for the faintest whispers from dark matter. Number 59, leading direct detection hunts. Deep underground, Xenon and T, Panda X4T, LZ, and Super CDMS watch for a tiny nuclear tap from passing dark matter. The large Xenon tanks now have multi-ton-year exposures and keep tightening WIMP limits with no confirmed hits. Super CDMS uses cryogenic silicon and germanium to chase lighter dark matter, complementing the Xenon giants. Each null result is powerful, carving away parameter space and guiding what dark matter can be. Number 60, Lux Zeppelin in one picture. Deep at surf, a mile underground, Lux Zeppelin sits ultra-quiet to dodge cosmic rays. Its heart is about 10 tons of liquid xenon kept near minus 100 centigrade degrees in a dual-phase time projection chamber. If a dark matter particle hits a xenon atom, it causes a nuclear recoil that releases tiny bursts of photons and freed electrons. Those paired signals let LZ pinpoint the interaction in 3D and separate rare WIMP-like recoils from the background. Number 61, it could show up in neutrino observatories, underground and under ice detectors like IceCube, Super Kamiokande, and KM3 Net Watch for faint flashes from neutrinos, perfect messengers for weakly interacting stuff. If dark matter annihilates or decays, it can produce neutrinos or other secondaries from places like the Sun or the galactic center. So far, there is no confirmed signal, but each search tightens the net. And a clean excess with the right direction and energy could reveal dark matter's nature. Number 62, we can rule out lots. Nothing found is progress. Underground detectors, sky surveys, and the CMB have ruled out huge swaths of dark matter possibilities. LZ and Z-non-NT silence slashes how strongly many WIMP candidates can interact. Gamma-ray hunts of dwarf galaxies squeeze annihilation ideas. The CMB limits early universe interactions. Add lensing and structure growth tests, and dark matter has fewer hiding spots. We are closing in by exclusion. Number 63, alternatives challenge dark matter. Some researchers test modified gravity ideas like MOND, which tweak gravity at tiny accelerations to explain galaxy rotation without unseen mass. These models can match many rotation curves, and relativistic versions were built to handle lensing. They generally struggle with clusters, bullet-style collisions, and CMB and BAO patterns that the dark matter model fits well. Work continues to test whether gravity needs a tune-up or invisible matter is still the better all-scale answer. Number 64, built to last. The CMB shows dark matter was already around in the early universe, shaping the first ripples before light could travel freely. Because it is so stable, we still see its imprint today. So its lifetime must be at least billions of years. Even if invisible, dark matter is a long-lived backbone of cosmic structure persisting from the hot Big Bang to now. Number 65, ghostly giants, heavy halos. Ultra-diffuse galaxies look faint and spread out, but some hide huge dark matter halos compared with their tiny stash of stars. Clues come from star speeds and rich globular cluster counts, which point to far more mass than the light reveals. A few of these wispy systems are dark matter heavyweights wearing a featherweight glow. Number 66, halos grow by accretion. In Lambda CDM, dark matter halos gain mass over time by pulling in nearby material and merging with smaller halos. Hierarchical growth. Simulations and merger trees show both smooth accretion and discrete mergers contribute with typical quantifiable growth rates. As halos grow, they fuel galaxies. Star formation histories closely track each halo's mass accretion history across cosmic time. Number 67, dark halos shape galaxy winds. Dark matter's deep gravity wells set the escape speed and channel gas flows. When halos grow massive, shock heating and gravitational energy from infalling clumps can stir hot gas and help drive outflows that starve galaxies. Feedback from stars or black holes supplies the push, while the halo's potential governs what is expelled or trapped, tipping systems from star forming to quenched. Number 68, simple shadow or hidden world. We do not know if the dark sector is one particle or a full family with its own forces. Some models predict dark photons and even dark atoms and molecules, making bound structures. Others keep it simple and collisionless. Cosmology and lensing set broad constraints, but many possibilities remain. Future searches probe portals like dark photons and self-interactions. For now, the only sure thing is its gravity. Number 69. When did dark matter appear? Two big ideas compete. Thermal relics form right after the hot Big Bang, made in the early particle soup, then freeze out as the universe cools. Axion-like dark matter forms later via the misalignment mechanism. A field rolls, and once the cosmic tilt sets in, it oscillates and creates lots of cold, invisible particles. By the time the CMB light was released, dark matter was already shaping structure. Number 70, where do we look for dark matter? Everywhere. Deep underground, xenon tanks and cryogenic crystals listen for tiny nuclear taps. In space and Antarctica, satellites and neutrino observatories hunt indirect clues from annihilation or capture. On the ground and in orbit, telescopes map lensing and galaxy patterns for hidden mass. Even colliders and precision tabletop tests chase faint portals to a dark sector. Number 71, biological dark matter. Life we have not found yet. Biologists use the term for the huge share of life we have not detected or cultured, especially microbes. Best estimates say there are millions of species overall, and possibly up to trillions of microbial species, far beyond today's catalogs. Modern metagenomics reveals this hidden biosphere by sequencing DNA directly from environments. No petri dish needed. Most of Earth's biodiversity is still invisible to us. Number 72, Oort's 1932 hints. Jan Oort analyzed how stars near the sun bob above and below the Milky Way's disk and found more gravity than visible matter could explain. He inferred invisible matter in our galaxy. The Oort limit, an early clue that some mass is not luminous. Later work refined his numbers, but the core idea, unseen mass-shaping motions, became a foundation for the modern dark matter picture. Number 73. Gravitational lensing sees the invisible. Gravitational lensing uses gravity as a detector. Mass bends light, so background galaxies look stretched or shifted. When that bending shows up where little or no visible matter exists, it flags dark matter doing the pulling. Astronomers map these tiny distortions to reconstruct mass, revealing dark halos and even cluster collisions where the gravity and the glow do not line up. We see dark matter by its gravitational fingerprint. Number 74, dark matter must be cold. If dark matter zipped around fast in the early universe, it would blur away small clumps and dwarf galaxies would be scarce. Observations show rich small-scale structure that fits slow-moving, cold dark matter that can clump and seed galaxies. Warm or hot possibilities are tightly limited by counts of dwarfs and by Lyman alpha tests. Number 75, dark matter cannot easily make dense objects. Unlike normal matter, it cannot radiate away energy. So it cannot cool and collapse into stars or planets. With no efficient interactions beyond gravity, it stays in diffuse halos instead of compact balls. Searches for compact dark objects also show they cannot make up much of the total. No dark stars or dark planets, just puffy, invisible halos. Number 76, dark galaxies with heavy halos. Astronomers have found ultra-faint, low-surface brightness galaxies, some with almost no stars or hot gas, that still stay bound, implying lots of dark matter. Candidates show up as HI-rich, barely glowing systems, and even as starless dark clouds lit by quasar fluorescence at high redshift. Extreme cases like ultra-diffuse galaxies can have huge mass-to-light ratios. Number 77, LHC missing energy clue. At the LHC, if dark matter particles are made, they slip through detectors and leave missing transverse energy. Physicists look for a single visible recoil. A jet, photon, Z, or Higgs, balanced by a big MET. That energy imbalance is the indirect fingerprint of invisible particles, so no tracks can still mean new physics. Number 78, cosmic cannibals leave trails. Big galaxies eat smaller ones, stretching them into long tidal streams of stars that wrap around the host. Those mergers do not just strip stars, they also peel off dark matter, leaving invisible streams alongside the stellar debris. We see tracks like Sagittarius and use them to map the host's dark halo and its past meals. Giant galaxies grew by devouring dwarfs. Number 79, dark matter drags the Milky Way's bar. The Milky Way's central bar of stars is slowing down over cosmic time because dark matter exerts gravitational drag on it. Patterns in stellar tree rings show the bar's spin has dropped by roughly a quarter since it formed. In theory and simulations, bars lose angular momentum to their surrounding dark halo, matching Gaia-era measurements. Number 80, invisible bridges and ghostly halos. Between Abel 222 and Abel 223, astronomers mapped an invisible bridge of dark matter using gravitational lensing. Light bends even where no visible glow appears. Galaxies sit inside huge gas halos where some of the missing ordinary matter hides, often faint, cold, or hot enough to evade easy detection. The cosmos has dark bridges threading clusters and ghostly gas halos around galaxies. Mass is there even when the light is not. Number 81, a rare no dark matter galaxy. NGC 1052 DF2 is an ultra-diffuse galaxy whose internal speeds suggest very little dark matter within its visible extent. Follow-up Hubble work firmed up the distance and the deficit, while leading models point to tidal stripping in its group as the culprit. A sibling case and simulations show interactions can peel off halos, leaving faint galaxies with unusually low dark mass. These oddballs do not kill dark matter, they highlight how the environment can sculpt galaxies in extreme ways. Number 82, AMS on the ISS, many events. No confirmation. Since 2011, the IMS-02 on the ISS has recorded billions of cosmic ray events, hunting for products of dark matter annihilation or decay. It sees intriguing features, but none can be confidently tagged as dark matter because other sources can mimic the signal. Many detections, zero confirmations so far. IMS-02 keeps tightening clues, not delivering a smoking gun yet. The net is narrowing even without a direct catch. Number 83, early and ghostly galaxies reveal heavy halos. In the lensed cosmic seagull, about 11.3 billion light-years away, outer rotation stays fast and needs a dark matter-dominated edge. Closer to home, the ultra-diffuse Dragonfly 44 looks faint, but once appeared to carry an enormous halo compared with its few stars. From the early universe to today's ultra-diffuse oddballs, galaxy dynamics keep pointing to unseen mass doing most of the lifting. The pattern is consistent across time and type. Number 84, Cosmic Ice 9, a speculative dark conversion. Some models propose dark matter could multiply by converting ordinary matter into more dark matter under hot early conditions. If true, it would briefly boost the dark sector, then shut off as the cosmos cooled, fixing today's mix. It remains highly speculative. Astrophysical tests such as neutron star heating already place strong limits on ongoing conversion. Interesting on paper, constrained in practice. Number 85, macros, dark matter might be chunky. Not every idea uses tiny particles. Some theories suggest macroscopic chunks from apple-sized pieces up to asteroid-scale masses. Many sizes are already ruled out by microlensing, seismic and meteor constraints, and old mica track searches, but windows remain where chunks could hide. If real, these macros would interact mostly by gravity. Acting like invisible space pebbles, the hunt checks both the very small and the very large. Number 86, new physics if dark matter is absent. If future data keep turning up galaxies with little dark matter and experiments stay null, we would have to revise the dark matter picture or lean harder on modified gravity ideas. Proposals range from MOND-like tweaks to emergent or extra-dimension frameworks that mimic dark matter effects without new particles. Current evidence, including tidal stripping cases and tighter detector limits, still favors some dark component. Any alternative must match clusters, lensing, the CMB, and BAO all at once. Number 87, speculative streaming invisible matter in our air. A controversial idea links stratospheric temperature spikes, atmospheric electron content, and even earthquakes to streams of unseen matter focused by planets. In this picture, unusually strong interactions would occasionally dump energy in the upper atmosphere, creating correlated anomalies. It is a bold hypothesis and not standard cosmology, so researchers tested against space weather explanations. So far, it remains unconfirmed and under scrutiny. Number 88, Lyman alpha galaxies trace dark fingerprints. Using more than 100,000 Lyman alpha emitters, astronomers map how galaxies cluster across cosmic time. Those clustering patterns act like fingerprints of where dark mass piled up, showing how galaxies grow with their halos. The statistics track the scaffolding beneath the light. It is a clean way to watch structure assembly. Number 89, the moon as a radio quiet ear for the dark ages. The far side of the moon is radio quiet. At about 50 megahertz, a lunar antenna could pick up the faint 21 centimeter signal from the pre-star dark ages. That signal's shape can distinguish cold versus warm dark matter by how it suppresses tiny structures. Earth's ionosphere and radio noise drown it, so lunar observatories are the prize. A moon-based array could open a new window in the first billion years. Number 90, atmospheric anomalies and streaming matter. Another version of the same speculative idea ties stratospheric temperature and total electron content to planet-focused streams of strongly interacting invisible matter. It is not standard, but proposed correlations are being checked against solar and geomagnetic drivers. The bar for evidence is high and requires repeatable predictive power. Until then, it stays a curiosity, not a cornerstone. Number 91, anti-helium candidates that would shake things up. Reports from AMSO2 include candidate anti-helium events in cosmic rays. If verified, one interpretation is production by WIMP, like dark matter. Surprising because standard processes make anti-helium vanishingly rare. Confirmation would be a big deal, but it is not yet proven and exotic astrophysical sources are still on the table. The jury is out. The implications would be strong either way. Number 92. Dark matter does not slow like regular matter. In cluster collisions, such as the bullet cluster, hot gas crashes, heats, and slows, but the lensing mass peaks track material that passes through. That clean separation between X-ray gas and total mass is a textbook sign that dark matter mainly feels gravity. Stars and dark halos sail on while gas is dragged. The contrast is a powerful diagnostic. Number 93, it could affect the first stars. Dark matter properties, such as annihilation or decay heating, can tweak cooling in tiny early halos and shift when population 3 stars form. Models show energy injection can alter molecule formation and gas temperatures, changing the minimum halo mass for the first stars. Evidence is theoretical for now. Observers are hunting signatures with radio and infrared probes. It is a frontier where particle physics meets cosmic dawn. Number 94, new lower bounds on dark matter lifetime. Analyses that see no decay signals translate into lifetimes of about 10 to the 25 seconds or more for many scenarios. That is far longer than the age of the universe and strongly constrains unstable dark matter ideas. Recent work pushed these bounds even higher using astrophysical data. Many faster decay models are now tightly limited. Number 95, light dark matter for odd galactic center signals. The Milky Way's core shows high ionization in the central molecular zone and a mysterious 511 keV line from positron annihilation. One idea is light dark matter that annihilates or decays into positrons, potentially explaining both without breaking other constraints. It remains unconfirmed, but tests are active across gamma ray, radio, and infrared bands. Either outcome sharpens what dark matter can be. Number 96, Hawking's primordial black holes, a tough fit. In 1974, Stephen Hawking suggested tiny primordial black holes from the early universe could exist. A 7-hour Subaru or HSC stare at Andromeda expected about 1,000 microlensing events if such objects made up all the dark matter, but only one appeared. That sharply limited many mass ranges for primordial black holes. Some niches remain, but not enough to explain everything. Number 97, 46 searches, and many methods. There are roughly 46 ongoing experiments chasing dark matter, from underground detectors like DEEP and LZ to space missions like DAM-P. Balloon flights like GAPS and the LAHC on Earth. Different tools, one goal, catch invisible matter by any trace it leaves. Diversity is a strength. Each method covers different mass and coupling ranges. Together they form a global net. Number 98, a Nobel with dark matter at its core. The 2019 Nobel Prize in Physics honored James Peebles for cosmology that cemented a universe dominated by dark matter and dark energy. His work helped establish cold dark matter as the baseline and shaped today's lambda CDM picture. The prize recognized theory that connects precision data to the unseen. It marked how crucial the dark sector is to modern cosmology. Number 99, dark matter in Star Trek lore. Dark matter appears in 5 Star Trek episodes. A memorable one is TNG's In Theory from 1991. The Enterprise encounters a dark matter nebula that warps space. A pop culture nod as real-world ideas are taking off. Science fiction and science moved in parallel, inspiring curiosity. The concept became part of the public imagination. Number 100, Philosophy by Starlight. Physics and philosophy meet. The data says something unseen shapes everything, and our models chase the right name. We infer dark matter from repeatable patterns, lensing distortions, galaxy speeds, CMB and BAO ripples. And those predictions keep checking out. In philosophy terms, that is scientific realism. Trust unobservables when they explain and predict consistently. Lesson from the sky, reality includes what works, even when it does not shine. And that's all. What surprised you the most? Leave it in the comments and subscribe. See you soon, your friend Neil.